Haritha ma'am. Ma'am, can you share your screen?
Yes. I hope you can see the screen.
You can see. So should we start?
Yeah, okay.
Okay, so welcome back everybody after tea. So we have Haritha C, and so we'll talk about round Frobenius theorem for a subshift of finite pattern. Okay, please go ahead.
Thank you. Hello, everyone. First of all, let me thank the organizers for giving me this opportunity to talk in this conference. So my talk is based on the work I did during my PhD period. So it's a joint work with my PhD supervisor, Dr. Nikita Agarwal. So it's on Perrin-Frobenius theorem for a subshift of finite type. So to begin with, Perrin-Frobenius theorem is one of the most celebrated results in metrics theory, and it has applications in mathematics as well as different disciplines. And also subshift of finite type is a very important class of dynamical systems, and it's used to model other dynamical systems, and several properties of subshift of finite type is relatively easier to study, and hence it's used to study the systems that models a subshift. And let me begin by defining or stating Perrin-Frobenius theorem. So it basically gives the existence of a positive largest eigenvalue and the corresponding eigenvectors, which have all increased to be positive. And Perrin proved it for positive matrices, and Frobenius then generalized it for a general class of matrices, which are irreducible metrics. So an irreducible matrix is a non-negative matrix A, for which for each ij there exists a constant k such that the ijth entry of a raised to k is positive. And for irreducible matrix, by the theorem, the spectral radius theta, known as the Perrin root of A, is positive and a simple eigenvalue of A. All the other eigenvalues of A have modulus strictly, not strictly less than or equal to theta. And then there exists a right and left Perrin eigenvectors having all their entries positive, and they're known as the Perrin eigenvectors. And if you assume that this k can be chosen irrespective of I and j, such matrices are called primitive, then then you get an expression like this for the asymptotic behavior of the powers of A. And this V and U are the right and left normalized Perrin eigenvectors. And this has application, this theorem has applications in graph theory as well, because if you look at 0-1 matrices, then an irreducible 0-1 matrix matrix is adjacency matrix of a strongly connected directed graph. And the Perrin root and eigenvectors play a crucial role in understanding the connectivity of the underlying graph. And also this theorem has applications in dynamical systems, and especially for symbolic dynamics. So you get expression for topological entropy in terms of the Perrin root. And also there is an important type of invariant measure on subshift, which is defined using this Perrin root and Perrin eigenvectors. And that will be discussed in the later sessions. So next, let me introduce the space that we are going to work on. So it's called the symbol space, and they're used to model a large class of dynamical systems. And the ingredients to define a symbol set are a symbol space R, a symbol set sigma, which can be finite or infinite, but in our case, we restrict it to finite case. And then the collection of infinite sequences with symbols from sigma. And let's see an example of how a dynamical system can be modeled using a symbol space. So for example, look at this map on the left-hand side. which is a map on the interval 0, 1 defined as t of x equal to 2x modulo 1. It's called the doubling map. And then to get a symbolic representation for each point on the interval 0, 1, what we do is we divide the interval 0, 1 into two equal parts I0 and I1. Then for each point in the interval, you look at the trajectory and look at the position of each Tn of x. So for each x in 0, 1, so you associate a binary sequence x0, x1, x2, and so on, depending on the orbit, the position of the orbit in this interval, whether it belongs to I0 or it belongs to I1. And in this way, you get a one-to-one correspondence between the binary sequence expansion as well as the points on 0, 1. And it turns out that for this particular map, it's the usual binary sequence expansion for the points on 0, 1. And also, if y is an image of x under t, then y will have a binary sequence expansion given by omitting the first entry of the sequence expansion of x. Now, for this particular case, what happens is any finite word you take, that's you can always get a sequence that contains this finite word. But then this need not be the case for a general dynamical system. For example, if you look at the map on the right-hand side, so let's say if you divide it into two equal parts as before, first 0 to half and half to 1, then you can see that none of the points on 0 to 1 are mapped to the points, are mapped to the interval half to 1. In the sequence expansion setup, you can see that that means the letter 0 is never followed by the letter 1, or in other words, the word 0, 1 is always forbidden in the sequence expansion. And that's where the subshift of finite type are defined, and they're defined precisely this way. So what we do is we look at a finite symbol set of entry 0 to q minus 1, and sigma n is the collection of all one-sided sequences. Then for a finite collection of words with symbols from sigma, which is f, subshift of finite type is defined to be the collection of all sequences in sigma n, where words from f are forbidden. That means they do not appear in the infinite sequences of words, and it's denoted as sigma f. And there is a map defined on the space, which is called the left shift map, which is obtained by omitting the first entry of the sequence. And the space is a topological space. It's a compact metric space with respect to the product topology, and the map sigma is continuous. And we make a small assumption, which is that the collection F is minimal. That means all subwords of the words from F are allowed. And we can always do this without loss of generality. And so this subshift of finite type is equivalent to a notion of directed graph, in the way that from a subshift you can always get a directed graph, and from a directed graph you get a subshift. And let's see how it's obtained. And so let's start with the directed graph, where V is the vertex set and E is the edge. And you define the adjacency matrix with respect to the graph, where it's a matrix of order Q, X, Y, the entry is 1 if there exists a edge from X to Y, and 0 otherwise. And then you define this subshift, where the symbol set is given by the vertex set, and the forbidden collection is given by all the words X, Y, where AX, Y is equal to 0. So it's called the subshift associated to G, and each sequence in sigma F corresponds to an infinite path in G. So from a graph, you get a subshift, and you can see that for this particular subshift, F will always have words of length 2, but for a general subshift, that need not be the case. F can have words of any length. And from that subshift, let's see how to obtain a directed graph. So let's start with the finite collection of words F, where length of the longest word given by P. Then if P is 2, then sigma F is called the one-step shift. And if all the words are of length 2, then you can define an adjacency matrix corresponds to the forbidden collection, and hence you get a directed graph. Now what we do is, if P is greater than 2, then you define a map that is one-to-one corresponds to a one-step shift, and hence then you get a directed graph and then an adjacency matrix. So how do you do that? We get that by defining a new symbol set sigma prime, which consists of all allowed words of length p minus 1. And the one-to-one correspondence is given as follows. So what you do is you look at the sequence expansion in sigma f, and the first p minus 1 entry is the first symbol here, and the second p minus 1 entry is the second symbol here, and so on. So since it's an allowed sequence, you can see that all these p minus 1 subwords will be an allowed word, and hence a symbol in sigma prime. And word of length p here will correspond to a word of length 2 here. Hence all the forbidden words can be thought of as a word of length 2. So when you have a subshift with words of length 2, now you get a directed graph where the vertex set is, so it's the directed graph associated with a subshift conjugate to this subshift. And how do you get that vertex graph? So V is the new symbol set, which is the collection of all allowed words of length p minus 1. And E is, there is an edge from one vertex to another vertex. So as you can see in this, so this letter symbol is followed by this symbol if and only if the last p minus 2 entry of this is same as the first p minus 2 entry. They're called, they overlap progressively. So once you have that property and once you join them, if it's an allowed word, then you say that there is an edge from X to Y. And once you're given, so in this way you can define a directed graph, and then from there you have an adjacency matrix. And note that this particular adjacency matrix will have order, or the rows and columns will be indexed by words of the allowed words of length p minus 1. And once you have the adjacency matrix, and if you assume that it's an irreducible adjacency matrix, then in the graph setup, what that means is between any two vertices, you can always find a finite path between any two vertices. And then entropy of this subshift is given by the logarithm of theta. So entropy is a quantity that defines the complexity of the system, and it's given by the logarithm of theta, where theta is the parent root of A. So studying the spectral properties of the adjacency matrix for associated with the subshift of finite type is important. And also this entropy is an invariant, it's invariant under conjugacy. So whatever systems that models a subshift, they also will have entropy that is given by the parent root. And our aim is to obtain a combinatorial expression for this parent root and eigenvectors. This combinatorial expression depends only on the size of the symbol set and this collection F. So we have to define some notion, some combinatorial notion depends only on the words from F. So so before that, here are a few examples. So you start with the full shift, and then it will have the associated adjacency matrix has size Q with all its entries equal to 1. And for F equal to, say, this collection, then vertex set will be the collection of all allowed words of length 2, and you get the corresponding adjacency matrix as well as the directed graph. So now we'll define this combinatorial object that I was talking about. So you start with two words U and V, where U is of length P1. Then the correlation polynomial is a polynomial where the coefficients are either 0 or 1, which are obtained in the following way. So you place W under U and shift it to the right by L digit, and then look at the overlapping parts. And if they match, then BL plus 1 is 1, and otherwise it's 0. So for example, if you look at UW as follows, then you have to place W under U and look at the overlapping parts. For L equal to 0, there is no, it doesn't overlap, and hence B1 will be 0. Then you shift it to the right by 1 digit, and then look at the overlapping parts, and you can see that they don't overlap. And then again, you shift it to the right, and now you can see that these two overlap, and hence B3 will be 0, and so on. So from this way, you get the correlation polynomial of U with W to be equal to Z cube plus 1. Note that correlation polynomial of W with U is different from U with W. And then Guibas and Odliscio obtained an expression for this parent root, not the parent root, this number f of n, in terms of the correlation between the forbidden words. So F is a forbidden collection given by A1 to AT, and then F of n be the number of allowed words of length n in sigma F. Then Guibas and Odliscio proved that the generating function for F of n, which is given by summation F of n z raised to minus n, will be equal to z by z minus q plus s of z, where s of z is the sum of entries of inverse of this matrix nz, where all the entries of nz are the correlation between two words. So ijth entry is the correlation of aj with ai, and so on. So this number f of n has other interest of its own. So one use is that the asymptotic behavior of f of n gives the topological entropy, and also it has applications in game theory and string overlapping algorithms and so on. And so now we have an expression for f of z in terms of the correlation between the forbidden words, and then we prove that this f of z is analytic outside the closed disk centered at the origin with radius theta, and theta is a pole for f, and moreover theta is a simple pole if you assume that sigma f is irreducible. So f has this form, and we prove that theta is a pole for this function, and also it's the largest pole that you can have. So consequently, what we have is that theta is the largest positive real zero of this rational function z minus q plus s of z. So we obtained an expression for the parent root in terms of the alphabet size or the symbol size and the correlation between the forbidden words. So for example, if you look at the star graph, so that is an undirected graph with one vertex in the center and n minus 1 vertex is connected to it. Then you have the collection of forbidden words to be given by this. And then you can calculate the correlation matrix polynomials and find the inverse of that and sum of entries of that. And solving this equality, obtain that it has the largest root given by square root of n minus 1. And another application is in game theory, which I think I'll skip for now. Yes, so we got an expression for the parent root in terms of the correlation polynomial. Next aim is to obtain an expression for the eigenvectors. So as before, it's irreducible subshift where f is given by this, and m of z is the correlation matrix, and ri with the sum of entries of ith row of n inverse, and cj is the sum of entries of jth column of n inverse, and ai tilde be some subword of ai obtained by removing the first letter of ai. Then if you look at this expression, note that u and v are two vectors indexed by allowed words of length p minus 1. And note that these expression depends on theta and the correlation of x with the forbidden words, and theta is in turn, that can be obtained from that expression that we had dependent on the correlation of the words. And these vectors u and v, we prove that they are the right and left parent eigenvectors respectively of A. And moreover, if theta is greater than 1, then this normalization factor u transpose v is given by theta raised to p minus 1 times 1 plus s prime of theta. So the proof of this is combinatorial. But proving this normalization factor required some techniques from ergodic theory. And once you have a normalized eigenvectors, this can be then used to define the defined an invariant measure on the subshift, which is important and has several unique properties known as the Parry measure. And also so this is for a subshift, but then for a given any binary matrix, you know that there is an associated subshift depending on the forbidden collection given by the 0 entries of the subshift. And that will have words of length 2, hence the expression for u and v are relatively simple, and that's given by this. So the correlation matrix MZ has linear polynomial on the diagonal with alpha either 0 or 1, and either 0 or 1 on the off diagonal. And you also use the property that when AI has AIs are all of word length 2, hence AI tilde comma x is 1 if AI ends with x, and otherwise it's 0. So once you use these properties to the previous expression, you get this simple expression for the parent eigenvectors for any irreducible binary matrix. And this is a simple example where Q is 2 and F is given by 0, 0, 0 and 1, 0, 1. And parent root is the positive real 0, largest real 0 of this, which is this. And then parent eigenvectors are also this. And I'll stop by talking. Thank you.
Okay, thank you very much, Haritha. Any questions? Online questions? No. So, thanks very much.
Thank you.
There's an announcement to make. There will be a conference trip to Pannudi at 2:30 p.m. So please return after your lunch.